Welcome back. The first video in this series explained the two cryptographic concepts that are fundamental to Bitcoin and other cryptocurrencies: hash functions and digital signatures. Now let's take a high-level look at the Bitcoin network itself, and then two fundamental data structures in the network: transactions and blocks. The Bitcoin network creates a digital currency called Bitcoin and enables transactions in Bitcoin. The Bitcoin network is actually just a bunch of internet-connected computers that are called nodes. A computer joins the Bitcoin network by downloading a piece of software called the Bitcoin Core from a trusted central repository and obtaining a copy of something called the blockchain. The Bitcoin Core contains the rules for the node to follow. Each node operates independently, but in accordance with these rules. The blockchain is just a bunch of blocks of data, with the blocks serially linked. Each block stores a bunch of records of past Bitcoin transactions. If you want to be able to make Bitcoin transactions, you can download onto your computer or smartphone a piece of software called a wallet. There are many different software wallets available for download on the internet. Your wallet can connect you to a Bitcoin node and provide a user interface to help you make Bitcoin transactions. The wallet also generates the public-private key pairs you will need for making Bitcoin transactions. These key pairs are generated from a very big number inside the wallet called a master seed. But wait a minute, don't you just need one public-private key pair? Yes, you're right, but it's more secure if a different public-private key pair is used for each transaction, and so this is typically what is done. It's important to realize that your Bitcoin is not stored in your wallet, nor anywhere on your device. Instead, your Bitcoin resides on the Bitcoin network. The wallet has the keys that allow you to control your Bitcoin. If you have a wallet, you will know that the wallet gives you a list of recovery words. This big number called the master seed is run through an algorithm to generate these words, and the words can be run through the same algorithm to generate the master seed. Thus, if you lose your device, you can download a compatible new wallet, and with that and the recovery words, recover your keys. It will therefore be apparent that it is really important you keep the recovery words, and also that you keep them strictly secret. The Bitcoin network also provides for the growth of the supply of Bitcoin. How does it do this? The network does this by awarding some new Bitcoin to a node whenever the node succeeds in processing a block of new transaction records, resulting in the block being added to the blockchain. This effort to process a block is called mining. Okay, that's an overview. Now let's take a closer look. Say Alice has some Bitcoin and wants to transfer some of her Bitcoin to Dan. The first thing Alice has to do is get an address for Dan so that after the transaction, it is Dan who controls the Bitcoin. You may recall from the first video that the address Dan provides will be derived from his public key. There are actually a few different transaction types used in Bitcoin which differ from each other in a few details. One of the differences between transaction types is how the recipient's address is derived from his public key. Let's assume we are using the transaction type pay to public key hash, P2PKH, which, as suggested by the name, takes a hash of the recipient's public key as the address for the recipient. Hashes were explained in the first video, and as will be recalled, the hash will ensure that the address for Dan is unique. To obtain this address, at Dan's request, Dan's wallet will generate a public-private key pair for this particular transaction, and then create a hash of Dan's transaction-specific public key. Dan then sends the hash of his public key to Alice. Next, Alice needs to create a record for this new transaction and send it to a node on the Bitcoin network so that it can be included in a block. The new transaction record is going to have to inform the node where on the blockchain to find the Bitcoin Alice owns that will fund the transaction, and will need to give the node the tools to allow it to confirm the Bitcoin really is Alice's. The transaction record will also have to include Dan's address, so Dan will end up with a Bitcoin. And the record will have to let the node know how much Bitcoin is being transferred to Dan. Further, the transaction record will need to include an amount that Alice is willing to pay to have the node process her transaction, as the node doesn't work for free. With inputs from Alice, Alice's wallet gets to work. Based on the amount of Bitcoin Alice wants to spend, Alice, or the wallet, selects an output in a previous transaction record on the blockchain which transferred Bitcoin to Alice. Now the wallet can create the new transaction record. The new record has a number of fields. By that I mean the record has a number of areas in which specific information is entered. One field identifies where the previous transaction output that will fund the current transaction can be found. This output from the previous transaction record is the input to the new transaction record. The identifier of the previous transaction output has two parts: a transaction ID, or TXID, which identifies the prior transaction record, and an index, which identifies the specific output in that prior transaction record. The Bitcoin from the specific output will fund all of the Bitcoin that will be spent as outputs in the current transaction record. The new transaction record also includes the public key that Alice used to generate the address which is stored in the output of the previous transaction record. At the first index in Alice's current transaction record, which is labeled index 1, there's an address for Dan, which is a hash of Dan's public key that he is using for this transaction, as well as the amount of Bitcoin going to Dan. This is an output of the current transaction record. At another index in her transaction record, labeled index 2, there's a pointer back to Alice. The pointer is a hash of another public key of Alice. At index 2, Alice records the change she wants back. This is another output of the current transaction record. By way of explanation, in a transaction record, if the amount of Bitcoin being spent is less than the amount of Bitcoin which is input, the difference will be kept by the node that processes Alice's transaction. For this reason, where Alice only wants Dan to get some of the Bitcoin from her previous transaction, Alice will direct most of the remainder back to herself. However, she will also intentionally leave a difference for the node to keep, as this acts as a financial incentive for a node to process Alice's transaction record. Indeed, the Bitcoin system requires that Alice offer at least a certain minimum incentive, but Alice can offer more to try to get her transaction record processed more quickly. In order to create Alice's digital signature for the new transaction record, the wallet first takes a hash of the data in the new transaction record. Alice's digital signature is then created from this hash, Alice's private key, and a random number R. Recall from the first video that the number R is also part of the resulting digital signature. Once Alice's digital signature is created, it is inserted in the new transaction record. The public key for the previous transaction, along with the digital signature, will be used by the node to confirm that Alice was indeed the recipient of the Bitcoin in the output of the prior transaction. Lastly, a TXID is created for the current transaction record. The TXID is a hash of all the other data in the current transaction record. The hash will ensure that the TXID for Alice's transaction record is unique. Once a transaction record is created, Alice's wallet sends it to a node, that is, a computer on the Bitcoin network. Let's call it Node 1. The transaction record is represented as a dark blue rectangle coming from Alice's device. When Node 1 gets Alice's record of the desired transactions, the node uses the TX ID and index Alice provided to find the previous transaction output, which will fund the current transactions. The node needs to ensure two things: that the previous transaction actually transferred Bitcoin to Alice, and also that Alice did not spend this Bitcoin before. In other words, that Alice is not trying to double spend the Bitcoin. How does the node do this? Firstly, while the node could use the TX ID and index for the previous transaction output to find the previous transaction in the blockchain itself, the node actually looks for the previous transaction in a local database of unspent transaction outputs, UTXO. The UTXO database stores the TX ID and index of each unspent transaction output on the blockchain, together with the amount of unspent Bitcoin and an indication of the recipient's address. The node keeps its UTXO database current through the mining process, which will be discussed in the next video. If the node finds the previous transaction in its UTXO, the second validity check has been passed, because the previous transaction would not be in the UTXO if Alice had spent the Bitcoin before. To check that this previous transaction output did in fact transfer Bitcoin to Alice, since the address of a recipient in a P2PKH transaction is a hash of the public key of the recipient, the node takes a hash of the public key Alice provided in her current transaction record and confirms it matches the address in the output of the previous transaction. But is it really Alice's public key? To answer this question, the node considers the digital signature that Alice provided. Node 1 takes a hash of the current transaction record and undertakes certain mathematical operations using this hash, along with the public key and digital signature Alice provided, to check if the number R is returned, as was explained in the first video. If the number R is returned, the node knows that the public key Alice provided is, in fact, her public key. And since the recipient address in the prior transaction output is a hash of that public key, the node knows that the prior transaction output did, indeed, transfer Bitcoin to Alice. If the validity checks are passed, the node stores the transaction record in its memory pool, labeled mempool, along with other transaction records it previously received that also passed their validity checks. Alice's transaction record is relatively small because it sets out just two transactions, one transferring Bitcoin to Dan, and a second sending the change back to Alice. Other transaction records may be larger because they set out multiple transactions. The usefulness of an index value to identify each transaction in a record becomes clearer in the context of a record with many transactions. After Node 1 validates Alice's transaction record, not only does Node 1 add it to its own memory pool of transaction records to be processed, but it also sends Alice's transaction record to other nodes in the Bitcoin network. These other nodes independently validate Alice's record and then include it in their own local memory pools and send Alice's record onto yet further nodes in the network. In this way, Alice's transaction record ends up in the memory pools of many or most of the nodes in the Bitcoin network. The number of nodes on the Bitcoin network varies with time, but is estimated to be more than 500,000. So Alice's transaction record ends up in a lot of places. The independent validation of Alice's transaction record by each node highlights a key feature of the Bitcoin network. It is, with a few small exceptions, a trustless system. That is, nodes do not have to, nor do they, trust other nodes. Since they don't trust other nodes, they independently conduct their own validity checks before adding Alice's transaction to their local mempools. So each of the nodes in the Bitcoin network has a mempool of transaction records. But how do the transaction records in these mempools get processed? The Bitcoin network processes transaction records in blocks of records rather than individually. Each block is of the same size and has a header for certain information that we will discuss in the next video, and an area for transaction records. Each of the nodes in the network creates a candidate block by copying transaction records from its mempool into its candidate block. A node has an incentive to stuff as many transaction records as possible into its candidate block because, recall, each transaction record offers some Bitcoin to the node that processes it. So the more transaction records in the candidate block, the more the potential financial reward for the node. The node will also look at what each transaction record is offering as a financial reward to process it in deciding what transaction records to include in its candidate block. If there are two transaction records of the same size in the memory pool, and one offers the node a bigger financial incentive to process it, the node will preferentially add the transaction record offering the bigger financial incentive to its candidate block. Indeed, if the network is busy, a transaction record that offers a small incentive may be repeatedly left out of candidate blocks, and in time may actually be dropped out of the node's memory pools and never processed. If, as is common, Alice's wallet program monitors the current going rate for processing transaction records, and Alice accepts its suggestion of a suitable amount to include in her transaction record, her record will not likely be ignored. So every node forms a candidate block. The candidate blocks of many of the nodes will be identical because their mempools are identical. But not all mempools will be identical, and so the candidate blocks of some nodes may be similar but not identical to the candidate blocks of other nodes. But why does every node form a candidate block anyway? Because the design of the Bitcoin network puts the nodes into competition. Only the candidate block from one node will end up being added to the blockchain, and only the successful node will get a financial award for its work. So it's a race to see who can get their candidate block onto the blockchain. Oh, and you might have noticed that the rectangle representing the first transaction record in the candidate block is shown as light blue. Why? Because the first transaction record is a special record called the Coinbase transaction record that's used by the node to collect the Bitcoin to which it's entitled if it is successful in having its candidate block processed. The Coinbase transaction record has the same fields as any other transaction record, but the input field does not point to any prior transaction to fund the Coinbase transaction. The output fields record the amount of Bitcoin to which the node is entitled if its block is processed, and one or more addresses to send that Bitcoin to. The amount of Bitcoin to which the node would be entitled is the sum of the processing fees from the transaction records in the block, plus something called a block subsidy, which is a certain amount of brand new Bitcoin. The rules for determining the block subsidy are simple. The subsidy started out as 50 Bitcoin, and the number halves after the processing of every 210,000 blocks. Currently, the subsidy stands at 3.125 Bitcoin. So how does this competition amongst the nodes work? This competition is undertaken by a process called mining, which is discussed in the next video. There will be a link to the next video here once it has been published, and you can also find the next video by subscribing to this channel.